Greetings all. So what I was actually working on previously was going back to using this reed switch in a pulse motor setup, and now instead of the reed switch doing a pulse from the battery, the reed switch would do a pulse from a cap, and then you would recharge the cap. And I actually made a bit of video on that, and the important thing is I got the code down so that, you know, when you move the magnet past, discharges and then recharges the cap. However, when I put it on the rotor, there's not enough oomph in the 10 UF cap to actually turn the rotor.
Yes. Yes, it's all coming back now. Ah, yes. I remember. Well, that feels good.
So not to be overly dramatic, but I need to put in a larger cap, and now I've got some additional solid state relays on order, and they'll be here soon. And I'm realizing I don't want monopole commutation, I want dipole commutation, so on and so forth. So that the logic worked, but it didn't work, and it will be made to work, I hope, going forward. But what I thought I would do then is go back to just the test bed of pulsing a cap into a coil in an LC tank circuit, and set up the Arduino as your data logging voltmeter. And getting the Arduino to function as a data logging voltmeter will be good both for, you know, characterizing the behavior of coils when you're pulsing, say, an LC tank circuit at different pulse durations, you know, like was being done before, where you're going through essentially a frequency sweep. However, well, I mean, mainly I just wanted to see if I could make it work. But also, just in general, data logging multimeters are not easy to come by. I mean, it's like, to get a good one, it's like a Fluke is like $600, and so you got to shell out a bit. And you know, I used to be able to get these things on sale for $5 at Micro Center. They're probably like $15 now, or 25 off of Amazon. But what I'm saying is that to get this down saves you some money. It has drawbacks of a bit less precision than a regular meter, and it can't measure negative voltages. But let's skip all that and just start going into how you build it. And so if you put Arduino voltmeter in Google, you get just dozens and dozens of these. And here's one off of DigiKey. That's where I ordered my solid state relays that are going to arrive from. And a lot of them, they make it too complicated because they're putting in an LED there. Don't need that. But they give you the code, and so again, there's one after another, after another, after another. So what do we want to do? And it's not at all much different than what we're doing with this thing, where you got a reed switch between a voltage divider, and when the magnet comes past, it changes the voltage that's shown up here. But to make a long story short, you have your A0 pin here, and you have ground there. So if we think about this for a minute, you have your ground here, you have your A0. Now this is running at 5 volts. That's the power supply for the Arduino. Now you can also tie it to an internal reference with the Arduino at 1.1 volts. I didn't bother to do that. I don't know if that makes I supposedly it might be a little more precise, but I didn't bother to. So you have, here's your ground, here's 5 volts. So now let's say you have a power supply and you put 2.5 volts here, what's going to happen? Well, if you read what's coming out of A0, this is a analog digital converter pin. So it's going to take any voltage between 0 and 5 volts and convert it to a number between 0 and 1023 or 1 and 1024. I'm not sure which, sue me. But it's got 1024 of those. I think it's maybe between 1 and 1024. So in other words, if you put 2.5 volts across here, you're going to see something like a value of 612 when you read what is coming out of your A0 pin, right? So now you want to take that 1 to 1024 and you want to convert it between 0 and 5 volts. So as we said, if you're at 2.5 volts, you're going to get something like 612. So what you do is first you take the reading here and you times it by 5 because it's 5 volts difference between 5 and 0, and then you divide it by 1024. And when you've done that, any voltage between 0 and 5 volts that you get here, then you can print it out. It's 3.2 volts, and so on and so forth. The problem that you have there is that if you go over 5 volts, then now you're just feeding power back into the Uno, and it's not going to like that. And if you're at 10 volts, you'll probably just fry that pin. So what do you do? What do you do? You make a voltage divider. So you have a resistor, and let's say it's 1,000 ohms. And here's where you measure things. So you put your voltage there to that end of the resistor. That 1,000 ohms goes to here. And then from there you have a 100 ohm resistor. And that 100 ohm resistor goes to there. So the 1,000 and 100 ohm resistors are meeting here. At the end of this 1,000 ohm resistor, you have one measurement, and here at the end of the 100 ohm resistor, you have the other measurement. So if you put a meter between here and here, and you are at 5 volts, it will measure 0.5 volts. So in other words, when you put 5 volts, boom, boom, what this thing is seeing is 0.5 volts. So now you do the exact same thing that you did before, and it's going to generate its number between 0 and 1024. You would times it by 5, divide by 1024, but now you times it by 10 again, because the voltage has been decreased tenfold. And now you can measure between 0 and 50 volts. And that's basically what I'm going to illustrate. And the last point I would make there is just that you can measure an arbitrarily high voltage. If you made this 1,000,000 ohms and this 1 ohm or something like that. However, this is an analog to digital converter that only gives you 1,024 different digits that come out. So in other words, if instead of measuring between 0 and 5 volts, you measured between 0 and 1,024 volts, you would only be able to measure 1 volt differences. So at 100, what did we say? 1,024, 1 volt, so 102.4.1 volts, 10 point, whatever it is, 10.24, you would measure 100th of a volt. So I guess you kind of get what I'm saying, is that this will be measuring between 0 and 50, and so the precision will be 1/20th of a volt. So good enough. It's free. So what do you want? All right, so let's see what we build. Serial monitor. This is like the most straightforward and simple explanation of this that I've found. And so, Arduino voltmeter. I'm sorry if the monitor is kind of looks a bit funny, but here you can understand it very easily and clearly. So you have volt equals what you're seeing on the analog pin A0, and then that's an analog digital converter that converts that volt that it's seeing between 0 and 5 volts. That's what the Arduino runs at, between a value between 1 and 1024, or maybe it's 1020. However, what if you don't want to measure 0 to 5? So here's how you would measure 0 to 50, 0 to 55 actually, and you just put in a voltage divider. So the first thing is to get that working. The second thing will be to integrate that code with this code where you're doing this, and get the measurement for here, send it out to the serial monitor, and then get the measurement for here, send it out to the serial monitor. And as I said before, you're going to have to pull the thing out when this thing starts to go negative so you don't harm the Arduino, and then you got to do that part by hand still. But this will be fun. It'll make it a lot easier to look at a number of things. So I guess, one of the first things that I want to look at, and I'm just thinking now, I'll probably run things at 10 volts. I might run them at 20, but if I run them at 20 and I'm not drawing the induction off anywhere, there's this spike that's just rattling around and it can fry stuff. So I'll probably run it at 10, but first not gathering the induction. And what you should see in this cap is exactly what was shown in the circuit simulator. You just have the thing oscillating between positive and negative, and when you're very far out, meaning very slow, it'll be a small oscillation. Then as you get closer and closer to the primary resonance, that's when you'll get the biggest oscillation. And depending on how much resistance you have in the system, it might oscillate from 10 down to negative 9 volts, and then to like positive 8.5 again, something like that. Then put this in, and you want to gather this again and see, does this change at all? And then you want to look at this and see, it gets these spikes at different places, and see, is there like some sort of way to line the two up and see what's going on there. Then try it with a different coil. Try it with a 100 UF cap, with a 1 UF, well, not a 1 UF because you wouldn't be able to get a reading, but 100 UF and even a 1000 UF electrolytic cap. That's one I'm really curious about. And I want to see, this should do about the same, although when you go to the electrolytic, there's going to be more internal resistance, so you're not going to get as good it's going to be a more damped oscillation. But, what I'm kind of curious about is, does the arrangement between where this thing starts to spike at different places and where this thing is, does that stay constant or does it vary? So that's what I can reasonably do now in a reasonable amount of time if I can get this thing working. And I haven't done that yet, so I'll shut up now. And the first thing to do will be to just get the voltmeter part working. So cut and paste a lot of this code. And then compare it to, just put a 9-volt battery on there and compare it to what it is here. And it might be a little off because, when I measure the actual, there's your voltage divider. And when I measure the actual resistance, this is like supposed to be 1K and it's like 997, and this is supposed to be 10K and it's like 10.4. But, that 11 value is just a constant. It's just the ratio here. So what you could do is, you could try to get precision resistors, But it would be a lot easier just, if you're off a little bit, then maybe this should be 11.1 or 10.9, and then it will match this more closely. So that's the first thing I got to get working on. And let me get that done, and then I'll get back to you, and then we'll make it go. Okay, so now we have an Arduino voltmeter. That's kind of neat. A voltage divider. And so, for instance, right now we're at 8.6 volts. And so if I put the meter on between here and here, where we're measuring between A0 and Arduino ground, instead of reading 8.6, it would read 0.86. And that's because we have a 10k ohm resistor here and a 1k ohm resistor there. One point I'd mention in passing is don't mix up a 10 ohm resistor with a 10k ohm resistor when you measure it. I did that. So this was kind of goofy for a while, trying to figure out what the heck's going on. Then I finally realized the resistors were wrong. So then, because you have these resistors, then you again adjust the voltage depending on what you're using for the voltage dividers. And so because all of that ends up at the end to be a constant, that you're adjusting the analog read value by a constant, I just put all that in, and I came out with, like 0.0537 or something like that. So voltage equals that. And then what I did was I put the meter here on the voltage, because that'll be more precise and accurate than there. And I saw, what are we spitting out here? And then I would adjust this constant until this and this match. And they nearly match now, 8.57, 8.58. You could try and do a little bit better, but you only have 1,024, and so you don't want to spend too much time trying to get that perfect, because it's not going to be all that precise. So what I'm saying is, you could measure, you want to measure real accurately what the resistances are, and then that would give you your ratio. But it's easier to just ballpark it and then put it on here and then make the two match up. So now let's see if it works through other voltages. So 15.15. That's not that good. 15.24. So it seems like it's not going to be consistent over the whole voltage range. 23.2 on the meter, 23.4 on here. I'm not all that concerned. What I'm mainly concerned about is getting the measurement at the right time. So even being off by this much is not, I'm not gonna worry about it too much, but I'll fiddle around and see if I can find a little bit better setup for adjusting the voltage. And I'm sure if I really knew what I was doing, there'd be ways to try to improve this more, but it's not bad. So now the only part left, and I hope it's going to be that easy, is instead of the probes going here to the meter, we'll put the probes to here, and then put that line of code in so that it's spitting out what this cap does, and then we just run that same program again, and we get our data logging voltmeter. Okay, so this is sort of the idea, but it's not working. And like, if here I don't have the Arduino hooked up as a voltmeter, and so we see it's going to 7.82. Now I'm going to stick the Arduino probe in, it's draining out of that 10k ohm resistor. But see, this is the idea. What I'm trying to do, get the pulse duration, get the capacitor voltage, get that lined up, and then you can just stick it right in a spreadsheet. So what I will try next is making this 1 megaohm resistor and that 100K. And maybe that'll work. If it doesn't, then I think this will not function as a data logging multimeter, because you're going to need enough resistance so the cap's not just draining out. Heck, I wonder if I have a 10 megaohm. But first, just see what it does with the Arduino with 1 megaohm, whether it reads anything. Well, son of a gun, this works just fine. So here's what I'm getting at. See, that's what you want. Now here we see one of those hills in the cap that's gathering, and we have the pulse duration written right next to it. And you can see here, okay, 14.38, 14.23. So not bad, good enough for government work. 15.78, 15.55. And see, everything's lined up. Now the other thing is, you don't need this like 2-second delay. You just need like a half second for it to write. Let me put that in. Okay, so that's what I'm getting at. You can probably even go a little faster than that. So now it doesn't take so long to get the data and to get it all lined up and pretty. So this is nice. Now, as I said, it's not going to work for the negative voltages there. So that part will need to be done by hand still. But at least you'll be in good shape with this. This makes things go a lot faster. That's all you got to do then, and set it up with different coils and caps. Okay, so here I've just sped it up some more, and it's it's plenty stable. You can see how fast that's going. So that makes this a lot quicker. And I'm going to see, just how fast I can go. But that's, that's going to be like a few minutes just to go through the whole thing. And you don't have to key anything in, and everything's lined up right. Your only worry is the precision of the meter, but it's good enough to see what the trends are. So yeah. And then what you do here, let me see if it'll work. I don't know how you would stop the thing, but what you would do then is you just go in and copy everything and then put it right in a spreadsheet. We have the first bit of data using the Arduino as the data logger. Then I went ahead and graphed it. So this looks like what we had before. It's just a lot cleaner now. And then I'm going to gather the stuff with the discharge cap and line those up and look at it. But already there's an interesting kind of thing that makes zero sense to me. And just to say, I'm not really going anywhere with any of this except for that it's a fun project to use the Arduino as a data logger. So there's not like any master plan here. I'm just looking at stuff and having fun. This is weird here, and it gets even weirder when we look at when it's data logging. And I've done this twice now. I'm going to do it a third time because it's like, wait a minute, that can't be. So instead of starting the thing at 32,000, I'll start it at 20,000 microseconds, and this occurs around 17,000. And let me just fire that up and show you what I'm talking about. So let's clear this out, and let's okay, so now we've started over again. We're at 20,000. 5, 4, 3, 2, and you can even hear it. Look at how much it's speeding up. And now it got to that one. And now look at the speed of it. Okay, let's do that one more time. This will be the fourth time. So again, there's no like, you have the final secret. I'm just saying, isn't this kind of weird? So as we're getting towards that point, it's data logging faster. And look how fast it's going. And now it's like, what happened? And now it's slow. It's 5 times slower. Now, I mean, if we look at the code, you can kind of see why that's a problem. Because all we're doing is taking this thing 40 times, and we're turning it on for that on time, and then turning it off. So there shouldn't be this huge discrepancy in how quickly it goes through. So that's why I'm saying, like, what you think you're doing and what you're actually doing might not be the same thing. It's not like there's something wrong here. It's just how the thing is behaving is not what's going on here. So anyways, I'm getting off topic. That was a fun thing. I don't know what to make of it.